Okay, so we turn to functions in this narrow sense. So we are narrowing down from relations to functions. So once again, that picture to keep in mind is this relations. Okay, and then there are functions. So relations, it's still about numbers, or not necessarily numbers, but right now it is. So relation between numbers, and then sometimes that relation is direct, or sometimes it's indirect. So functions are direct relations in that sense that you see on the left. So functions are direct relations, or also another word to use is explicit relations as opposed to implicit. So x squared plus y squared, there is a relation then, but it is implicit. So how do we get x from y from x? We don't know, maybe. Or maybe we do, maybe we don't. We can figure this one out. We did figure it out last time, how to handle this thing. But in general, the formula might be so complicated that you will be unable to extract one variable from it and turn it into an explicit relation. But suppose we could, and that's the starting point when we do have that ability to get y from x. Okay, how? Well, we don't point that out just yet. What we do is we say, as I say here, we say that this is a black box. Okay, so black box. A function is a black box. So what's inside, we might not know necessarily. Okay, so it's important not to concentrate on that too much. So the only requirement that makes something a function is here. There is only one y for each x. So you plug in x, no matter what it is time of the day, it will give on the other end the same number y. Okay, so assuming these are numbers. So the only problem is that it is depending on some other circumstances. Then you cannot call it a function anymore. But other than that, we expect it to have to produce the same output for the same input. Okay, so that's another way to put it. Same output for the same input. Okay, so why black box and why not something specific? Because there are many interpretations to begin with, and we'll examine them shortly. But also, it is okay not to. It might be okay not to know. So it could be. Maybe you literally don't know. How about this? Maybe. Oh, here's an example of a function for you that I brought up last time, I think. So you have your income here, and the function is represented by the IRS, and then your tax bill is the output. How they do it, maybe you don't know. Maybe you don't know all the intricacies of tax law, but somehow that income turns into a tax that you're supposed to pay. Assuming, once again, it is the same income, produces the same taxable income. How about that? Produces the same tax on the other end. What is the formula? Maybe there is no formula. Maybe there's a list of instructions. So what's inside is happening is not important as long as it is understood that there is no conflict and there is a same input will produce the same output. Okay, so you don't know what it is. Maybe you are imagine you are a boss and you are just to tell your employees to compute this function, even though you might not yourself know what that function is, but as long as they do, you're fine. So it's not necessarily absolutely know what's inside. So, for example, x on the input, and then on the output you're supposed to have sine x. So maybe you don't remember how to compute sine. Doesn't mean you give up. As long as you know that sine is a function, then at least there are many questions and answers to be provided for that function, and you treat it as such. So the list of functions is long, and at the same time it is always incomplete. So there is no point really to concentrate too too much on specific functions. But rather it is more better idea to think holistically and as if there's infinitely many functions beyond the horizon, and you don't know what kind of functions you're going to encounter. So you have to think of them in the abstract. So there's a function, that's what it does, and then the only thing is you might be worried about is what is the output versus input. Okay, that's what's happening. How it's happening? Maybe we're going to be building these boxes a lot. And so that just to get experience, but it is possible that there might be nothing specific given to you. So we certainly know that it is 9 out of 10 that function will be described by a formula, but it's not 100%. Okay, so formulas. Their list of describing or interpreting functions is long. Number one is an algebraic formula. Another one could be a computer program, for example, so which is not necessarily has a one formula, but it is a sequence of computations or steps that produces the output. The graph, another way to interpret the function, and another one is these data. Okay, so there are formulas there, as you can see. I actually point out for you what that formula is. But suppose you don't have a formula. It's still, you might be supplied with this. Let me like this. Nope. Okay, so that you might be facing nothing but data, 2 columns of numbers, and one column is the inputs, the other outputs, and that's the whole story. Where they come from, maybe there is a formula there, maybe there is no formula there. So you can imagine that's another interpretation of functions, is just the column of inputs versus column of outputs. So there might be no formula. Maybe there is some kind of detector that 1 minute of time takes the temperature. Okay. There is no formula there, but it is a function then. So every moment of time, or every second of time, for example, the temperature is recorded. Okay, so you have seconds are listed in the first column, temperature is listed in the second column, and you have your function. So it is a function, you treat it as a function, but there's no formula. There's no formula, there's no algorithm for computing one from the other. All of these are possibilities, and the graph is on the right. Okay, so that's another way to see functions is when there might be no data given, but maybe you can read the data from the graph. Okay, so then once again there is no formula, but there is an algorithm of recovering the function from the function that you see. So all of these angles we'll have to take care of and see functions in multiple ways. But we'll start with the simplest one, not the simplest one. Well, let me actually start with the most common, as I said, is algebra and a formula. But let me start with this. So a diagram, or in fact a flowchart, probably a good way to put it. A function is a flowchart. How does it become a flowchart? It is possibly a sequence of steps. So here's an example of such a thing. So X is the input, and then step number 1, add 3. Step number 1. Then the output, maybe we're done. That is a function, but maybe multiple steps. So the second step may be multiply by 2. Okay, and then when as many steps as you can imagine, square it. Okay, and they could have you can have insert numbers of variables here if you like, but the point is the input is you take the input and you carry out these 3 operations in this succession, and then at the end there is one number. There is no formula. Or at least at this point, there is no formula. It is the function. What function does is it just described verbally. So nothing wrong with that. As long as it is unambiguous, then you're fine. Okay. So I mean, there would be no trouble for anyone seeing this instruction to compute this function for every x. So you have x. I have 1, right? I have 1. then add 3. So I'll have 1 plus 3, the output will be 4. 4 becomes the input of the next function, so it's 4 times 2, and the output becomes 8, which becomes the input of the next stage, and I square it, so I have 64. So 8 squared is equal to 64, so the final result is 64. So then the 1 is the input, and 64 is the output. The rest are intermediate steps. Okay, so once again, there is no formula. There doesn't have to be a formula. As long as any kind of sequence of instructions, as long as it's unambiguous and there are no data coming from other directions, then you're fine. Okay, so you can imagine that every box over there is replaced with something else. There are issues for us to worry about. Remember the domain, whether if I replace that square over there at the end, I replace it with the square root. You know, there's a possibility that you're not supposed to take square root of a negative number. What if I have division somewhere? Then they might end up dividing by 0. So all of these things we'll have to watch out for. But generally, it is we will figure it out. Okay, so the input, output, that's a function, an example of a function. But then you certainly can just take it as a starting point, and you can flowchart number 1. Okay, the number 1 interpretation or visualization of a function is through flowchart. The second one is as we know 9 out of 10, and that's an algebraic formula. And I think once you get to more complex formulas, you realize that probably if it's your responsibility to compute the function, probably this is better. Number 1 is better. Flowchart, it tells you exactly instructions how to do it unambiguously. It is the formulas that frequently is misread. The order of operations sometimes is confusing. So there are some rules that you have to remember and follow them to the letter in order to compute everything correctly. But instructions, it's like we took that formula and spread it out in order for you to do not to make a mistake. And that's what you do with computers. You give them instructions that are unambiguous. So let me take that example, and I just express y in terms of x. So y is equal to x plus 3. So that's a formula. I'm getting y from x by an explicit algebraic formula that happens to be simple. If I go into the next box, I have what is it? Z equal to, well, let me turn it around. So the x is the input, then x plus 3, that is y. Okay, so there's a match between the box and the formula, and the output is y. But at the next stage, y becomes the input, and I have y times 2, let me put it here, y times 2, that is my, what's happening inside the box, and then the output is z. Okay, so the list of instructions is gradually turned into algebra. Algebra will be more compact, but that we pay price for that. And finally, I go to z squared, and that is equal to w. So that is a 3-stage affair. Carefully, it has to be linked. That's why I like those arrows, because it tells you in what order and things progress. And so here, this y becomes the input of the second formula, and this z ends up over there. Okay, so if you want to speak in terms of computer programs, you would say input output. You'd say consecutive operations. If algebraically, what do we call this? Those arrows over there would what? Those arrows. So x plus 3, I found y, and then what do I do with that y? What does that arrow supposed to represent? It is a function, but what is the algebraic operation? Algebraic step, substitution, right? The word is usually used as substitution. So we are the output of the previous step, we substitute into the next. So this substitution, this also substitution. So in that sense, what I carried out over here was exactly that. It was a substitution. We carried out the one step, we took the output, and then substituted into the next formula. Okay, so that works out just fine if you want a list of instructions. But this, what I have still, is still a list of instructions, even though each of them is given algebraically. But what makes a difference, I have 3 formulas. Ideally, and that's usually what you want to see, and when you represent a function by an algebraic formula, it is a one formula rather than several. So can we make it into one formula? And the answer is yes, and the answer in the how, once again, substitution. So we substitute one into the next, and we'll have one formula. So that way, we're going to get rid of those variables that were disposable. Y and Z were disposable variables, or they were going to be right now. So I take that y is equal to x plus 3. Okay, so that y ends up to be multiplied by 2. So I just take this expression, and it's going to be over here. So I have x plus 3 times 2 is equal to z. So one substitution has been carried out. Okay, and so instead of 2 formulas, in the beginning I have 1. Okay, and y is gone. But then I do it one more time, and that z is substituted over here, so I have x plus 3 times 2 squared. See how generous I am with parentheses? And you can also see where those parentheses come from. They come from substitutions. So there would be no ambiguity about in which order operations are carried out. Just have as many parentheses as possible. All the confusion comes when the people try to omit some. There seems to be too many parentheses, and then you have to think about what is the order of operations. If you have all the parentheses there is no ambiguity, and there won't be any doubt in what order to carry these out. So this is the end result. The end result, and once again, you see these parentheses, and the explanation of order operations sometimes goes in the wrong direction, and you tell which operation comes to do first. Whatever it is, the first one is parentheses, then powers, or something like that. But really, if you look at this, the idea is kind of a different. The idea is it's outside from inside out. Inside out order. If you want to recover the steps of operations that in that final formula over here, you might want to think about it as if you carrying them out inside out, from inside out. From inside out. So in other words, what is the operation that is most inside? So it's like a box wrapped in several wrappings. So unfortunately, you have to deal, and you are on the inside. So you're trying to work your way out, and so you are X, okay. And then what do? You first add 3, then you are done with these parentheses. You multiply by 2, and then you're done with those parentheses, and you square it. Okay, so in fact, I could write it this way. So say X is the input, then the first operation is plus 3, and then we end that computation like this. Now let me use different color again. Okay, so parentheses indicating the end of the step. Okay, then I multiplied by 2, maybe like this, multiply by 2. Okay, then I am done with this step again, and then I squared like this. Okay, so once again, you see where this formula came from. It came from that long flowchart with 3 stages. You should be able to work your way back as well. So that's what I try to indicate in this formula, which is certainly more compact, but much more compact than the flowchart, and that's the attraction. The attraction is that this is much shorter, especially if you start to removing parentheses, and then it will be even more compact. But the point, however, you still have to be able to work your way back and recover, reconstruct the flowchart. Okay, so that's what all the concerns about what is the order of operation in algebraic formula is. how do you turn it into a list of instructions for computing that formula? So there is no some other purpose of that. If you have a function to understand it, to understand a formula, you should be able to carry it out step by step as a function. So x plugged in, you carried out sequence operations, you have y, the output. Okay, so that's why it is so important. But just remember that there is always a flowchart somewhere behind it, behind every formula. So let me maybe do that once as an example. So say so I'm taking a formula, x squared minus 3 square root plus 5. Okay, so suppose this is my function. And, well, there is no doubt, I hope, about the order operations, but once again, it is the point I'm trying to make here is that you should be able to turn it into instructions for yourself, for somebody else, or for a computer from the algebraic formula. The computer nowadays certainly can compute these functions, no problem, but at the bottom, if you look under the hood, they actually do this. So the end result of every program is a sequence of operations. Okay, so every computer or calculator ultimately deals with those. So let me just try to, well, with your help. So x is the input. What's the first step? From inside out, square it. So as much as possible, make those steps as simple as possible. So just square it. That's the first operation. Okay. So what do I do with the output of this? Subtract 3. Okay. Next one. Square root. And finally, add 5. Okay. So there might be more complex formulas than that, but basically it is the whole story is here. Okay, so and it allows you to sort of break something complex into smaller parts. For example, it is quite possible that you don't really know how to take a square root. You know how to add, you know how to subtract. You know how to square numbers. You just multiply by itself. But maybe you just don't quite understand what square root is. But at least you have extracted it into a separate piece. So this piece might be questionable. But first of all, you know it's a function. Square root is a function itself. And secondly, you sort of can delegate it to somebody who knows how to do it and figure out and carry out that computation. The rest is you understand, and at least you know one piece that may need some attention. Okay, so now, so back to algebra. What is our concern with algebra? The notation is complicated, and on its surface is all. This is what I'm talking about. That's all there is. But there is so much confusion about it that there might be. It's worth talking about just about that little formula. So let me now do something simple. So the notation. So we might be looking at f of x equal to x squared. Okay, so one of the simplest imaginable. In fact, maybe y equal x squared. Yeah, that would be the full description of a formula or a function. So what are these letters? Let me. These are all names. So it's, apart from x squared, everything else is just about names. So names, y is the name of the dependent variable. Once again, it is a name. Whether or not there is a number behind it, that comes later. But on the surface, it's just the name of the dependent variable, also known as the output. And then the same applies to x. It is a name of the independent variable. And actually, f is the name of the function. Okay, so that applies to what's happening, what's to the left. So x reappears in the formula. Once again, the name of the independent variable. It's a label. Okay, so until you start doing any kind of algebra with it, it is really literally a name. I'll label it in just to distinguish x from y or x from u, and or other situations. You might have different variables present at the same time, so you just want to name them, put a label on each of them, so there would be no confusion. But at this time, nothing really happens until you reach to the right hand side, where you might think of x now as an actual number, as not an actual but a number, but unknown number. Okay, and then you might carry out some operations with it. But at this point, it's just the notation itself, which is what's on the left, is entirely about three names. So the parentheses, maybe, I don't know if they deserve special attention, but as you can see, it is they serve an important role. And sometimes you can actually, sometimes you might encounter, you say function, a text like this, function f. Okay, so you might see something like that, which indicates that you are speaking of f separately from its independent variable. Okay, so f is indeed the name of the function. It could be function f, could be function, say, sine, cosine, or whatever function you can think of. It might be a specific function, or maybe a function that is not, such as f, an abstract function. So it does appear separate from everything else, from y or x. So what the parentheses serve, they serve to separate the independent variable from the rest of the formula, if any. And it is you can think of it as some call it the funnel of what, of our function as a black box. So as if this is how you insert it. So I'm not sure if I can exactly try to reproduce, to make a picture here. So that's a funnel. Okay, so you put something in. Remember, x is the input, so you put it in. Okay, and then this funnel goes on, and then what? And then somehow, or maybe it turns around, and there's a 1, the output. So this time it's not a black box as much as some kind of a machine. Well, there is a black box somewhere in the middle, but the point is there's a funnel in, funnel out. Okay, and so as you independent variable, it's not that the variable is independent. It is you can independently plug in any values of x that you want into this funnel, and it will produce, depending on that, the variable of some new number y will appear at the other end of this machine. Okay, so as you can see, what I'm trying to suggest with this picture, that's what the parentheses serve. They serve kind of separate that variable, point out where that variable is supposed to be plugged in. Okay. Similarly, it is in fact it kind of is similar to what you see on the right. We usually prefer to use the word substitution as I indicated. It's not working. Okay. But it is similar. So let me try to suggest what that means. So x squared. How do we interpret x squared? Once again, you can think of it as a funnel like this, x squared. So this is the funnel that x is replaced with any number you can think of. And you, in fact, if you actually want to carry this out, this is algebra. But if you want to do it in a kind of a way that is the easiest way, probably you leave a gap. You leave a gap like this. Okay. So that's the same thing. But what the advantage of the last one, it's not an algebra, it's not a formula, but it is literally of the idea of plugging in works, because there is a place where I can say put 3. Well, like this. Okay. I can put any number there, and I will know what that function does. Okay, so it will be 3 squared. That's how I compute the number. The answer will be 9. Okay, and then once again I erase this. I erase this 3, right, and I plug in another number, 5. Okay, and then well, I know what to do with 5 squared. It might seem like a silly exercise, but you can think of full functions that are more complex and might require, I don't know, 2x squared minus 3x plus 7 over x cubed minus 5. Okay, so that might be your function. And once again, to understand what's happening here, you might once again replace each x with some kind of a entry gates. Okay, and then inside of that gates you will be plugging in x. So 2 gate squared minus 3 gate plus 7. So here's multiplication here, divided by gate cube minus 5. Okay, so there is only one input, so that input will reappear in each of these 3 spots. Okay, so whatever number you have, you put it in all 3, and then you don't have a formula what's on the left. What's on the left is a formula, the abstract formula, algebraic formula, when you have that variable, that label that appears, and you have to think of it as if it is an actual number, just happens to be unknown. Okay, that's the challenge of algebra. On the right, however, remember that's what it's ultimately about. Functions is that your ability to compute this formula for any number that you plug in. Okay, so if it is x, then there might be nothing to compute. But when it is a number, you will end up with a specific formula, and then hopefully you can carry it out and find the number at the end of that computation. So this is how, in fact, we can match these up. So f of the gate, that little square. Okay, so on the left we have a traditional algebraic representation. On the right it is the interpretation that you probably should not write as much as you should have it inside your head. Okay, so whenever you see the formula on the right, what should appear to you is what you see on the right. Okay, so windows, well, you can think of these as windows where that number is becomes visible. Okay, so whatever number you put here, remember that's the crucial part, is also explains the notation. What's the meaning of notation f of x? That's what the explanation. There's this opening, and inside of the opening you put a number, and that you repeat that number in each of these 3 instances. Okay, so if it is 2, then that 2 should reappear in every of these instances, and then there are no x's to worry about. You have an actual formula that you just compute. Okay. So that's the meaning of the notation of algebraic notation for functions. So once again, name of the function followed by the name of the function followed by the name of the variable in parentheses, which might be replaced with a specific number, or might be replaced with that's where difficulties start with another function. Okay, so remember the way we did it. We already did it in the previous example, like this. So this is a function, but then its variable becomes its input becomes the output of the previous function. And so you can have then a bunch of function like nested inside of each other. So that will be discussed later. For now, we'll just stick with simplest kind of functions. So then we are proceeding. So we have these 2 ways to represent functions. For now, the flowchart, and which might not have formulas in there. So that's what we did here. So as you can see here, I intentionally used just the word, so that would be unambiguous and non-algebraic. But you can have algebraic formulas as well. It's not really of any challenge as well. So x, and then the output is x squared. Well, is equal to y, then y comes into the next one, so it will be y minus 3, which is z. Then z comes into the next one, and a square root of z, and that is the output of the last, not just yet, and then that input of the next one, and then w plus 5 that is the last one, say, the output of u. Okay, so once again, it is a sequence of steps. It just, you express it verbally or you express it algebraically. It's the same thing, right? Okay, so data and graphs, that's the third approach. They are kind of overlapping, but probably we'll look at them separately as much as we can. So number 3 is data. In a way, that's what number 3, data. That's what we started with. That's how I try to explain functions in the very beginning. It is nothing but inputs and outputs listed. They typically in algebra they are certainly numbers, but they don't have to be. Okay, so if I can find that picture. This one maybe. So that's where we started with the arrows. That's a function in the end, but that we ended up in this line. It's a kind of an algebraic representation once again, which I just talked about. But then the stage we're reaching in now is this, representing, well, not this one actually. It is a table of values between inputs and outputs, and they put across if they are related to each other. The one that I was referring to, is not here. Show me just a minute, maybe here. I guess I didn't do a lot of that. So let me just write it out. So you can have for 1, 2, 3 as the input, 4, 5, and here 0, 1, 1, 2, 5. And these are the outputs. Okay, so that is a function. So where did this number come from? I made them up. It's still a function. Okay, so as long as the correspondence is unambiguous, and once it's put in writing, of course it is unambiguous, then you're fine. You have a function. Okay. The only things to worry about is always what is the domain, what's the codomain, do we get everything? So that's the biggest challenge is with representation functions by data, is that the data is always incomplete because it's a list. And the list might be infinite, or even worse, as we saw previously, what you might ask, what is the value of 1.5? So 1.5 between 1 and 2, and even if you insert a number here and you say 1.5, well, the value is 0.5. Okay, great, but then between 1 and 1.5, there is still a gap, and is there a value there for us to worry about or not? You should know. It is for most of the time, it's up to you to build that function, so you should know whatever the domain you choose is it. Okay, so it's just if if data is incomplete, then you create more data, but then you have a new function. Okay, so that inserting new values into that table is creating a new function because I'm changing the domain. Okay, so once again, domain here and codomain. Okay, so once again, if we go look here, ignore. So you look at the first two columns. The first column is x's. The second column is y's. And the point of this is remember that concern that we're supposed to have. Is there one output for each input? Or can you have two? How do you know? It's very easy to have if you put your x's in the order. Okay, then it is really easy. So if they are at random, when there is no structure, such as some data that has no structure, but if these are numbers, put them in order, and you just, by examination, you'll see that there are no repetitions of x in that column, and then you know that it cannot be nothing but a function. Okay, so whatever's happening in the next column is not important as long as in the right column, in the left column, you don't have repetitions. So this is what I mean. It is hypothetically possible to create a table like this with, say, 5, 7. Okay, so that if I have this extra row here, what's the conclusion? What? It's not a function. Because because number 5, the input number 5 has 2 different outputs, so that cannot be a function. But because they were in order, it was very easy to detect. If I put that line 5, 7 in the beginning, it would be very easy to not to notice, and then you would know if it is or it is not a function. Well, fortunately, if you do it by numbers have structure, they have order, so they can be ordered by hand, or Excel will order them for you. So it will be just to rearrange the rows in such a way that a column that you pick will be put in the proper order. So there you go. It's very easy to make sure that the function is the data. What is it? It's just a 2 columns of numbers. Okay, that's what the function is. 2 columns of numbers. That's a function, except only when you verify, what is it? Let's say with no repetitions in the first column. Just to keep it simple, make sure that there are no repetitions in the first column, then you will definitely have a function. Okay. So and then you proceed from this point. You proceed to graphs. So that would be number 4. We just talked about graphs and where they live. So literally, they would proceed from data to graphs, because graphs is built based on data. And this is an example of how it happened, how a computer does it. So once again, let me, if I highlight this chart, it tells you what data has been used. If you use the first and third column, so then the purple column is the input, the blue column is the output, and these, if now you go horizontally, you have 2 coordinates, and those 2 coordinates are plotted. Okay, and then it creates a dot on each of the for each of them on the XY plane. Okay, so that's what we have been talking about. So that's what computers do for you, but you should be able to, as we have discussed, you should be able to plot these by hand as necessary, as well as read them off the chart. So at 1 it is 0, at 2 it is 1, at 3 it is 1, at 4 it is 2, like that, and 5 is 5, maybe here somewhere. Okay, so I plotted these 5 points on the XY plane. So that's a graph. So that, in a way, it is what I just did. It is a transition from data to graphs, but we should be able to read the graphs and extract data from it. Okay, so we will also have talked about that already. So every point has 2 coordinates, and those 2 coordinates then form, what do they form? Say, what does this is a 5, 5, say, hypothetically, what does it form? It forms a row in our table. Okay, so they might be in the random order here, but if you read them one by one, put them in the table. You will have that data. The only thing is to ensure that this condition that I just put here is satisfied. There are no repetitions in the first column. That's the data. How do we express the same idea on the for a graph, for a bunch of points on the XY plane? So once again, a function is, so that's 4th representation of functions. Points on the XY plane, but there is that X restriction. What form does it take? That restriction that we have over there, I underlined it over there. How you can detect violation of the rule. That is a function. You detect it by noticing that there might be two rows in the same table. How do we detect this problem on the graph without actually doing any data? How would you know that there are a bunch of points? So far, that's all I have written. my function is represented by a bunch of points on the xy plane. It will be a function provided what? Okay, so that's right, but can you make it more, the visual? That you can say that. So there are no 2 points lying one under the other. So this is not allowed. Okay. So so in other words, with no 2 points, well, located one under the other. So it's just more geometric way of putting what I had over there. No 2 points located one under the other. It is indeed frequently called the vertical line test. So the points, you don't have to have 5 points. At its simplest, it's 5 points. In general, you can have a curve and you have infinitely many points. So in that case, that interpretation of the vertical line test is better. You can actually detect easier. So suppose these points, I still speak of points, but suppose there are many of them, maybe like this. These are the points. Is this a function? This is not a function. So all of these green points do not form a function because if I try to draw a vertical line over here, I will discover, so this is vertical line, I will discover that there are 2 points, one under the other. That's what I discovered, right? So that's what the vertical line test tells you. So you can think of maybe this one. Okay, so this one does pass the vertical line test because this is fine, and even this one is fine because when I put, you remember what it means to when I put a hollow point there, it means that the point is missing there. Okay, so as you can see that dot, the heavy dot is included and the empty dot is not, which means that the vertical line test is still satisfied. Okay, so next time we'll talk about domains.
I got a question.
Yep.